Right. So that's the topic for today. I don't think that I already uploaded the lecture notes. I will do that today so that you can read afterwards the theory behind it. Quality control. So that's the topic. Actually, I'm going to talk about these type of control slides. Now, you understand now why I first need to introduce the system diagrams, system behavior model. This is what I'm going to talk about. Right, this type of control. And the idea would be, so here is, I'm not sure whether we have mathematicians in here, people who like to address things more precisely. So if you want to be a bit more precise, the output of this system, the output, let's call that Y. Why? I don't know. That's usually what we do in mathematics. In the Netherlands. Yeah, why not? Exactly. By the way, so this is one of the things that I noticed, right, with you international students studying here, that the way that we describe things in mathematics in the Netherlands or in Western Europe might be a bit different than in other parts of the world. Or actually, I think also in France and Italy already, you use different letters. The logic is the same, right? It's not like we have our own mathematical logic. It's the same logic. But for instance, we usually describe a function as y is a function of x. Y is fx, something like that. And if we explain a line, and it goes up with a slope, we usually say y is a plus b times x. That's the way that we do things. But I noticed that in different countries, you might use different letters. Of course, the message is exactly the same, right? There's nothing different in there. So, if you don't recognize it right away, I'm sorry, I try to apologize. This is the way that I express usually things. So y is an output. Y is the output of this process, whatever it is. And it's a function of several variables. Right? That's what it says. There's several things that we can choose, like the speed of the machine, the tolerances in there, maybe the type of material, something like that. Okay, so y is a function of x1, x2, x3, etc. A lot of variables that are influencing my output, y. Okay, so the output could be, I want to measure my a product characteristic or a process characteristic, something like that. That's the result, right? And the x's give me the input. And if I want to influence my y, I need to do something about those x's. That's the idea. That's the logic. Now I'm already in control theory, what I'm doing right now. That's already a bit of control. You can already see, so I want to measure those x's and then adjust them in order to get the right y. That's what I do in the control slide, right? I measure my x's to adjust them in order to get the right y at the end. And hopefully I understand the f. Hopefully I understand the function. Now don't worry, I'm not going to do a lot of mathematics. Well, a bit. We'll see about it in a minute. So one of the things that that quality control is, if you think about quality control, the first thing probably that you think about is do a test on the final product. I do a test on the final product, I check with specifications, and then I say it's okay or not okay. Something like that, right? Okay or not okay. So that's an inspection, a final inspection as a filter, which is okay, but it's not the best way of controlling quality in your process. The thing is, in the end I'm selecting, but I'm still creating maybe the mistakes, right? So what creates the mistakes in there, I don't solve it by doing quality control in here. I need to check earlier to see where my mistakes are appearing, right? If I really want to prevent them in the future, I need to do something else. But this is at least my customer might expect good things. So it's better than doing nothing, right? It's better than not doing a check. All right. But this is not a high level of quality management that we're talking about. It's only doing the inspection at the end. There's always a problem, by the way, because the inspection sounds like I never release a product that's wrong, and it also sounds like I never reject a product that's okay. We will see that that's not true. You will always release products that still have mistakes, and you will reject products that are actually good. It will happen. The only thing that you hope is that the amounts are not that high. It's limited.
Is that because of human mistake, or
sorry?
Is that because of human mistake, or?
No, it's because the inspection itself is also a process.
Yeah.
And it makes also mistakes. So any process makes mistakes. So also an inspection process could also make a mistake.
Can you give an example?
Yeah, if you do a visual inspection on a bottle,
Yeah.
right, and you want to see if there are scratches on it. What if you missed one scratch? It's possible, right? It's only done visually. It might be true.
So
Of
we-
course, there are people who are trained to do this, and but still, they might still make a mistake. They miss one.
So can we do inspection for inspection and then we review?
Yeah, you could. They are doing that. They are doing that. Yeah, they are doing that. They're testing, for instance, the inspectors or the way that they do the testing. You can test the way that you do testing.
Testing.
Yeah,
That's the test.
yeah. And then you could even test. Well, there you go. That goes a bit further right. But you could. Yeah. All right. So this is, and of course it's firefighting. Actually, it's preventing a fire from happening. Actually, in the end, instead of preventing things. So it's better to do inspections throughout the process at different steps, because then at least you know earlier if there's a mistake. But it does mean, by the way, that you have to have specifications on what you need to check over here. So not only in the final product, but also on the intermediate products. We need to understand what is it that we want that we need to inspect in order to understand whether it's okay or not. But still, we're only doing it by inspections. But you test things earlier on. All right. Okay. Now the thing is, that's the second reason why we always make mistakes, is that we always think, well, firsthand maybe you already realize that a specification is only one number, which is not true. It's not true. There's no specification that's exactly one number, and it's only that number that's exactly completely okay. For instance, take a look at these 1, 2, 3, 4, 5 products. Well, if you're not from the Netherlands, but then you definitely know already the first product, right? Hagelslag, right? Chocolate chips. Here you go. This one over here. There's a weight on there. See that? 390 grams. It should be 390 grams in there. It doesn't say it's always 390.00000000000. You might think that's true, but it's not true. It said 390, plus or minus something. Okay? And it depends on plus or minus how much it differs, whether we still think it's okay or not.
For example, can it be 388 because
Yeah, good.
there is a correction error?
That could be, yeah.
Plus
Yeah. So if it would be really nice if you have a detailed scale to weigh the weights, use it, right? And then see what the differences are between those packages. You're going to see differences.
Plus minus 1 grams or not.
Some, for instance, yeah, that might be true. Yeah.
For example, in the calories and the nutritional aspect, there is a 20% margin of error.
There you
so
go.
a lot of brands overestimate how many
Exactly.
how much protein or how
Exactly.
much things they have. So
Same goes for the diameter of a tennis ball, right? There are norms for that, but these are tolerances. They're not one number. It's not always exactly that number of millimeters. It's plus or minus something, right? Same goes for what is an A4 paper? If you cut paper on A4 size, is it always exactly the same? Well, if you go detailed enough, it's not going to be always the same. There's always going to be some tolerances in there, plus or minus a bit, content of a bottle, color of a car, you name it. Whatever characteristic of a product, we think usually that should be only one value. In reality, it never is one value. It's always an area, the tolerance area, that we find if it's in between, it's still okay. And if it's not in between, we don't think it's okay. Something like that.
And I want to say that some of them are specified right on the product and some are not, but you have to look for you have to look up the law to see if
Exactly.
But for example, it reminded me of tennis rackets, seeing the tennis ball, and on most of them you see they have a plus minus 7 grams
Okay.
to their weight,
Right.
except for the ones which make them exactly the same gram. Most of them, but it says directly on them.
Yeah.
But then on food or something like that, they usually don't specify that.
Well, there might be a signal, a European norm on there, so like an E statement in there, which specifies a bit on what kind of tolerances they would allow in there. So there are specifications on that. We'll get back to that in the last class that we're going to have. We're going to talk about the European norms. The thing is, Toguchi, I told you that we're also going to look in Japan. It was one of the Japanese in Toyota. He was one of the earliest who discovered the idea that actually there's no such thing as only one perfect okay product. I mean, you have usually a tolerance. As long as you stay within those limits, you should be okay. So it's not one point where it's okay. It's not like 1 or 0. It's okay or not 0. Actually, what he says, well, look at the orange, right? This is the best one. This is still okay. This might still be okay. At some point, we say now it's not okay anymore, right? Now it's outside of the specification limits. So what he says is instead of having only one value, we have specifications levels, upper and lower, USL, LSL, upper specification limit, lower specification limit. And if it's in between, we consider the product as being okay. If it's not in between, we consider it not being okay. Well, here we have another reason why sometimes, in inspection, we say something is okay, which might not be okay. If we say this one is okay, and if you open it up, you see that actually already a part in there is already kind of rotten. You wouldn't see that if you would use time as a measurement, right? But this is what to push, and he calls it the loss function. What he says is actually there might be one optimal value, maybe that's true. So that's the one with actually the lowest loss in quality. But it doesn't mean if I go from the optimum, I don't accept the quality. There's going to be a loss in quality, and the further I go away, the more I lose my quality. But it's not like I can't use it anymore, right? So there might be an optimal point, but going away there, as long as I stay within my lower and upper specification limits, I would still be okay. I still find it acceptable.
And it also happens in stores that you discount because they're about to expire.
Could be true. Yeah, you could. Yeah.
But that's also always dependent on the product. Right?
Yeah, it depends on what we're talking about.
How
Yeah.
do we find those lines where it's...
Well, where would you look for? Who decides on whether something is okay or not in the end?
The customer?
The customer, I think, right? Yeah. So the customer. So it depends on what the customer finds acceptable, which is true, by the way. If you think in some environments a particular product might not be considered okay, while in another one it might still be considered okay. That really depends on the environment, on the customer. Yeah. So the customer, but it depends a bit, of course, on whether the customer can really specify. Usually the customer can't specify the limits, so you need to help the customer to specify where are your limits. As for instance, you could try, right? Let him try and then see whether he finds it acceptable or not. Yeah.
No, I was gonna ask. If you could give another example where those specifications are used.
Well, yeah, all the products that I just shown you, like the weight in a box of cereals. Right? There's a kind of an optimal weight, but you don't want to do less. Maybe upper, you still accept a bit more, right? As a customer, you wouldn't mind, but you're not gonna buy 2 kilos if you only want to have 1 kilo,
Yeah.
right?
Okay. But it's always specified by the customer, right?
It's related to what a customer wants. Yeah, yeah. And so it's the usage of the product actually by the customer that determines what the specification should be. Yeah. So the traditional view was always, as long as I'm between these, I'm optimal, and then suddenly I'm not optimal anymore, right? I suddenly have a hope. That's not true. In reality, it really looks like this. It's like a continuum, right? It's not like 0, 1, right? Okay. Anyway, that's what the Taguchi explained. And the thing is, if you look at our processes producing those products, again, these processes will never produce exactly the same. If you drill a hole in a plate of metal, the diameter of that hole, if you measure it carefully enough, in enough details, is never going to be exactly the same. There's always going to be some kind of a difference between the two holes. Doesn't have to be a problem, but there is a difference. You need to go detail sometimes to see it, but it is true. So in any process, any production process where we have machines that do something, you're going to see variation. That's nature, right? The machine shows variation. There he goes, right? And if you measure something, you might see, for instance, in time, here you see a measurement of something, a weight of something, I don't know what. in time of a bag, filling of a bag, we see in time the changes in the weight, right? So this process apparently has some variance in the process. It doesn't mean that my process is not controlled, right? It might still be okay. If it stays between certain limits that I have, I might still think I'm doing good, right? But it always will show a variation. Make sense?
Yeah.
All right, cool. If this is true, I'm not sure how much statistics you already had. Then you can calculate an average, can't you? Right? Everybody can calculate an average of these numbers right over here, right? That's somewhere over there. Right? You add them up and you divide it by the number of observations, and then you got the average. Right. This is the average value. Okay? And you see that there's variation. So this process has this average weight, but there's variation up and down. All right. So there's variation. See that? Every dot has a distance towards the average. I can check all those distances and I can calculate the average of those distances. The larger the average distance, the more variation I have, right? And the higher the peaks and the lower the peaks, the longer the average distance is going to be. So the average distance of those dots to the average is a measure for how variable my process is. Make sense? Okay? So in this case, it would be look at the orange arrows and I simply calculate how long these arrows are and I calculate the average of the length of the arrows and that gives me an idea of how much variation I have. Okay, almost this is done in statistics. Almost like this. Not exactly. I'll show you how it's done. Because in statistics, and I don't think that you already had it here in university, but you may have had it already in your previous educations. We use the term standard deviation. Do you know this term standard deviation? Who knows the term standard deviation? Okay, about half? Something like that. Okay. Anyway, I'll show you. Don't worry too much, right? We're not going to do all kind of calculation of standard deviation. But you need to understand the concept of standard deviation. Because standard deviation actually is a measure for how long these arrows are. So if you understand, this is what you need to remember. Standard deviation is something like the average distance of all the dots towards the average. The larger the standard deviation, the more these dots go up and down, right? Then the average distance is going to be large. So it's a measure for how much variation I have in my process. Okay?
One question.
Yeah.
But sometimes it could be this way is not true because when you measure 10 times, let's say, and let's say that the tolerance that you have is not big, but could be like the one of them could be like very up or down.
True. True.
So actually, you just have like 10% like a Viking, but the rest.
Okay,
is
of course, you know what, you need to drag this along a long time and do a lot of those measurements in order to really understand what really is the average distance, right? So this is just a sample, just a short. You need to look at all of them to really understand what the average distance would be, including the ones that are really high.
Yes.
Yeah, of course. Yeah. But this is the idea of standard deviation. Standard deviation is something like the average distance, which is a measure for variability. For those who like mathematics, this is how you calculate things. The average is calculated like that. I'm not sure whether you recognize that. It's the value of all the x's. And I have n observations, so this gives you the average. And then, how do you calculate standard deviation? Well, you don't start to calculate standard deviation. What you do is, you first calculate the distance squared. So every dot to the average, the distance, and you square that, and then you take the averages. Right? That's called variance. So we got two concepts that you may not know. Variance, standard deviation. Variance is the average distance squared, which is true. That's the average distance squared. This is how you calculate the variance. It's the arrows, but then squared. Which means that the larger arrow is multiplied more than the smaller ones. So if you have some large ones, that's going to create an increase in your variance, right? It's the average distance squared, but it's more or less similar. It gives you an idea of how much. And then, this is variance. The standard deviation is the square root of that. And if you take the square root of average distance squared, It sounds like average distance, right? It sounds like. It's not exactly the same, but it doesn't matter. For now, it's good enough. Right? So remember, standard deviation is something like the average distance of all the dots to the average. And it is a measure for how much variation I have in my process. Okay.
Is standard deviation like bad, having a high one? Or should we aim
Yeah.
to have it?
Yeah. In one of the things that we industrial engineers should be doing, I think in many cases, we're trying to reduce variation in processes. Yeah. We
So
can't
it
get
stays
rid of them, by the way.
as
Zero
stable
is
as
probably
possible.
impossible, but we try to reduce them because it makes it harder to predict what's the outcome, right? If you have a lot of variation, it's going to be complex to predict what's going to be the result.
That's why there's mechanization.
Sorry? Yeah, well,
Make it more
but still in
predictable.
mechanization is going to be variation.
Yeah.
Even if you
more
mechanize.
predictable than labors.
Labor has more variation usually than a mechanized process. Yeah, an automated process again is better than a
Yeah.
mechanized process, but it still has variation. There's no process without variation. All right, got that standard deviation idea? All right. Then check the normal distribution. Hope the sound works. No, not yet. Why is the sound not working? Hold on. Do I need to connect something? Is there a cable in there? This one? No, that's not the one. I think it should be possible to. No, it shouldn't seem to. Let me try. Otherwise, I'm going to explain myself.
In this video, we'll be learning about the normal distribution and the 68, 95, 99.7 rule. When we talk about normal distributions, we refer to data we get from a population or sample. So before we actually talk about the normal distribution, we need to first distinguish the difference between a parameter and a statistic. A parameter is a number that describes the data from a population, whereas a statistic is a number that describes the data from the sample. Examples of parameters and statistics are the mean and standard deviation. But because of the definitions we just talked about, we have to be very careful with what symbols we use to represent these numbers. When we are dealing with a sample, we use the symbol x bar to represent the sample mean, and we use the letter s to represent the standard deviation. These are statistics. When we are dealing with a population, we use the Greek letter mu to represent the population mean, and we use the Greek letter sigma to represent the population standard deviation. These are parameters. The population parameters mu and sigma are very important when we talk about normally distributed populations. So what is a normal distribution anyways? A normal distribution is a special type of density curve that is bell-shaped. For this reason, the normal distribution is sometimes called the bell curve or the normal curve. The normal distribution describes the tendency for data to cluster around a central value. In fact, this central value is the population mean mu, which is always located in the middle of the curve. So for any normal distribution, we can say that some data points will fall below the mean, other data points will fall above the mean, but most of the data values are located near the mean. The normal distribution and its shape actually arises from many different variables found in nature, such as weight, height, volume, blood pressure, and many more. This is why the normal distribution is commonly studied. For example, exam scores are known to follow a normal distribution. Some people do great on exams, some people do poorly on exams, but a large majority of people score near the average or the mean. In this example, the average exam score is 50 because it is located in the middle of the curve. Now that you know what a normal distribution looks like, we need to talk about the population mean mu and the population standard deviation sigma. Both of these tell us important information about how the normal distribution looks. We'll talk about the population mean mu first. The population mean mu characterizes the position of the normal distribution. If you increase the mean, the curve will follow and move towards the right. And if you decrease the mean, the curve will still follow and move towards the left. This happens because the data will always cluster around the mean in normally distributed populations. As a result, the value of the mean determines the position of the normal distribution. On the other hand, the population standard deviation sigma characterizes the spread of the normal distribution. The larger the standard deviation, the more spread out the distribution will be. And the smaller the standard deviation, the less spread out it will be. Notice that when the spread increases, the curve gets much flatter. And when the spread decreases, the curve gets taller. The reason for this is because the normal distribution is a density curve, and the total area of any density curve must remain equal to 1 or 100%. So changes in the width of the curve must be compensated for by changes in the height of the curve, and vice versa. Overall, here are some points about the normal distribution. The normal distribution is unimodal. This means that the distribution is a single peak. The normal curve is symmetric about its mean, so you can clearly see that the distribution can be applied to the equal points. The parameters mu and sigma completely characterize the normal distribution. The population mu determines the location of the distribution and where the data tends to cluster. The population standard deviation sigma determines how spread out the distribution will be. The notation given to a population that follows a normal distribution can be written like this. Although it looks scary, it means what it says. For the variable x, it follows a normal distribution and has the mean mu with a standard deviation of sigma. Now that we've been introduced to the normal distribution, we can talk about the 68, 95, 99.7 rule. If we were measuring the heights of all students at a local university and found that it was normally distributed with a mean height of 5.5 feet and a standard deviation of half a foot or 0.5, we can construct a normal distribution as follows. From here, we can create intervals that increase by the standard deviation. So we'll have 6, 6.5, and 7, and on the other side we'll have 5, 4.5, and 4. So what the 68, 95, 99.7 rule says is that within one standard deviation away from the mean, it contains a total area of 0.68 or 68%. Because of this, we can say that 68% of the population are between 5 and 6 feet tall. And if you go 2 standard deviations away from the mean, it contains an area of 95%. This means that 95% of the people in the population have a height between 4.5 and 6.5 feet. And finally, within 3 standard deviations away from the mean, it contains a total area of 99.7%. This means that for the population we are studying, 99.7% of the people are between 4 and 7 feet tall. Now you might be wondering, what happens if we go 4 standard deviations away from the mean, or 5 or 6 standard deviations away from the mean? And to answer that, you actually can. A normal distribution actually never touches the x-axis. It continues on to infinity. So you can go as many standard deviations away from the mean as you want, but the area contained within these regions will be very, very small. The 68, 95, 99.7 rule is a great way for approximating the areas of a normal distribution. And this works for any normal distribution, no matter what shape and size. So let's do some practice.
No, I'm not going to do that. Did you get it? The idea?
I have a question.
What you need to realize is that the y-axis, so I'll come
So it's always one bar is 68 and next is 95.
in a normal distribution. If my population is normally distributed, if the observations that I do are normally distributed, then yeah. And in many cases, in many situations, they are normally distributed. That's nice. In many processes, you have an outcome which is normally distributed. And what you need to realize. So this is the value. In the y-axis, you see the value. Which value, like the heights, right, of a person, something like that. And it's they are in feet, but now in metric system. Like what would be the average heights? 175, something like that. 170. In the Netherlands, maybe 175. I don't know, but something like that, right? Or let's say it's 175 meters. And we have a standard deviation, right? Something like that. So here we have the values, the different values, and here you have the frequency. How often do we see something like that? That's the frequency. And what it says, so it's called an histogram. We'll see histograms later on. What it says is that most of the people are around here. If you count, most of them are around here. A few of them are a bit over there. Oh, something like that. There you go. something like that, right? So you count how many people do have that value, and that's where you create the bell-shaped curve. This is the frequency distribution. So that's the distribution that they show. You had a question.
But for me, if you're doing, for example, Otto on height in the student university,
Yeah.
it's going to be impossible that someone is 10 foot or 12 foot. So shouldn't there be a point where the line ends? Because it's impossible
Yeah, in reality, yeah. Well, impossible.
for someone to be 10 feet
Well,
or 12.
I'm not sure the largest person in the world. Does anybody know how tall the largest person in the world is? How much? Sorry? 221?
No.
I think it's maybe even more, right? I think it's over 2.5
That's like 3 meters.
or 21 feet. Or 321. All right. I don't know. It goes far, right? But it's true that in reality, of course, there is an end in normal cases. The distribution is not, because it's a mathematical formula. So the formula doesn't end. In reality, there is an end. There is a lower limit and an upper limit.
it depends on the people that
reality.
you did the
Yeah,
tour.
exactly. Yeah, but it's still, this distribution usually nicely fits most of the situations. Yeah. Right. So if you would draw, all right. So let's take a look at this diagram, the one that I showed you with an average and with the where I showed you the. It could be true if you would count, if you would put them in classes, or so how many are nearby this and near the average, further away from the average. That in the end, if you create a frequency distribution, it might look something like this. So that's the idea. This is the normal distribution which fits what you see in dots right over here. Okay. So and the idea of if it fits something like a bell-shaped curve, like the normal distribution, already know, and if we would know the average and S, the standard deviation, S is the standard deviation, if we would know that, if we would know the average distance, remember that? Then we can already explain, without actually doing a lot of more observations, we can already explain the entire distribution. It looks something like this. That helps a lot, right? It already helps me in understanding what this business is about. All right. Okay. Now, why do I present this? First of all, because I want you to realize that variation is crucial. Variation, often it's more important. Variation is more important than the average. Because we have more problems with variations in many cases than with the average. Which makes sense if you think about it, right? Most of the issues are in the outer skirts of my observations, right? The longest or the shortest one, the most filled one and the least filled ones. The best students, right? It's not interest them anymore because they're really on top of everything, or the lowest ones where you think, how can I put something like that, right? It's the outer skirts that usually are the crucial, the important ones, the difficult ones. If you look at a process from a quality point of view, because I'm returning now to quality control, I'm looking at a production process, and I want to know, am I still in control? But the question is this cyclist still in control? It's motorcyclist. Right? So it depends, of course, if you're going to do this, he has a very tight tolerance, right? You shouldn't do a bit too much variation, because then you might have, this might be a consequence, right? If you're out of control. Question is my process still in control? That's a crucial question. So we're talking about process control. Okay. Now, let's take a look at this instrument for whether my process is in control. In quality control, they often use something like a control chart, this one. And it applies the idea of average and standard deviations. Check this out.
Hey everyone, and welcome to the Engineering Toolbox channel. Today we're talking about a very powerful tool known as a control chart. What exactly are control charts and why are they so useful? My goal is to answer those two questions in this video. Before I get into things, I want to pose a question. Here we have two charts where I've plotted output data from two different processes over time. Both data sets have the same scale, 0 to 100. My question to you is, are these processes in control? Or is one in control and the other out of control? By the end of the video, I'll tell you the answer and why.
Oops, sorry. But now you're awake, right?
So the first piece of understanding control charts is understanding variation. There are two types of variation, common cause variation and special cause variation. To help us understand these concepts, let's use an example. Think about the time that you get to work every day. Is it exactly the same time? Or would you say you usually arrive between a certain range of times? Say you usually arrive at work between 7:45 and 7:55, with an average time of 7:50. This range represents common cause variation. It is predictable. In other words, your boss can count on you to arrive in this time range, as long as the general process stays the same as. But what if your car breaks down? You definitely aren't going to make it to work within the usual time range. This type of scenario represents special cause variation, where there is some atypical cause that leads you to arrive at work way later than usual. Luckily, your boss uses control charts, so as soon as 7:56 hits, he knows something is up and he calls. After you tell him what's happened, he sends a cab and a tow truck and you make it to work even though you arrive much later than usual. Alright, I'm only joking about that. Hopefully your boss isn't using a control chart to monitor when you arrive at work. If that were the case, I'd say he has some serious micromanaging issues, but you get the point. So control charts help us separate and visualize common cause variation and special cause variation. And that's really what separates control charts from your basic run charts or time series plots. But how exactly do we determine what is common cause from special cause? In other words, where do we draw the line on what amount of variation is considered common? Because as we talked about, there's always going to be some amount of variation, but the key is determining how much variation is abnormal. So this is where things get into the statistics, but don't worry, I'll keep things somewhat light for now. Basically, some people that are much smarter than me have come up with ways of determining where we should draw the lines between common and special cause variation in the process. Those lines are called the control limits. The upper and lower control limits are determined first by calculating an estimated short-term standard deviation or sigma value based on the data set used. Standard deviation is just a measure of how spread the data is. Then we add 3 standard deviations above the mean and subtract 3 standard deviations below the mean to set our control limits. For a process that is generally under control, we can then say with some degree of confidence that if a data point falls outside these control limits, then there must be some special cause driving that excess variation. Another concept
Do you understand that, by the way? The probability that it drops outside is very low, right? Out of the sigma. It's the 99.7%.
Signal and noise are really just terms for how we categorize the data on the chart, where signals are points that are outside the control limits and noise are points that are inside the control limits. So basically, special cause variation is what leads to a signal, and common cause variation is what just creates noise. And you may also see these terms used interchangeably. So knowing what we know now about control charting, let's go back to the question that I posed at the beginning of this video. Are these processes in control? And the answer is yes, both of them are in control. And I know that because I actually put these to test with my control charting template that I built in Excel, which I'll link to that video in the description. And when I did that, all the data points are in control. In other words, the variation is all common cause for just noise. But we can actually almost see this just visually. The data in both plots are up and down and all over the place, but the amount of variation is consistent around the mean and therefore predictable.
This is important what he's saying right now. What he says is both of them are in control. Right? Because what he did is he measured both processes and he calculated the average distance, right, the standard deviation, for in this situation, and he calculated the one in this situation, which apparently the process that you have is showing this variation. That's the natural variation of the process. Every process has a natural. This is the natural variation of this process. And as long as I stay within plus or minus 3 sigma, three times the standard deviation of the average, I assume I'm still having the normal variation. There's nothing extraordinary happening. So in this case, I'm still okay. My process is still showing the natural variation. Also true for this one. Of course, we see a difference between the processes, but it's because they're different processes, right? This is a different process from this one, right? But it only shows the process control is about, is my process still showing the normal expected variation? That's what it does. The UCL and the LCL are showing that. Is my process still showing the natural variation? It's not connected to what a customer wants. He doesn't discuss what a customer wants, right? He doesn't say specification levels, he says control levels. Is my process showing the normal behavior of this process? That's what process control is about. We want to know, is there something broken, something extraordinary, then it jumps up out of the control levels. Then there's a signal that's a problem. As long as I stay within, I assume there's no problem with my process. Okay? That's crucial. All right. Well, I'll skip the rest. Otherwise, we're going to take too long in there. So that's the idea of this process chart. It's called statistical process control, SPC, statistical process control chart, or control chart. And you see here, there's an average. This is the average, and you can calculate this, the average distance from every dot, right? You can calculate the standard deviation. Don't worry, I'm not going to ask you to do that in an exam or something like that. Later on in statistics, you're going to learn how to do that. You apply the mathematical formula that I showed you. That's the one. But I'm not going to ask you that. I'm always going to give you the standard deviation of a process if I ask something about that. And plus or minus 3 sigma, that's where you have the control limits. And as long as all my observations remain within the upper UCL and the LCL, I'm okay. I assume that my process is not showing any extraordinary behavior. The assumption is it still works fine. Okay? That's what it does. Okay?
How do you get a sigma?
Observations.
Oh.
Look at the history. You know, you measure the things in the past, and based on that, you can calculate what is the average distance, right?
Yeah.
That's how you would do that. Okay. All right. The type of charts that you would use. So what is the axis and what actually you put in here depends a bit on, because you could measure it, for instance, on distance or something like that, or diameter of holes or whatever. That's a continuous kind of measurement, right? It could be points, some 0, 0, 0, whatever. You could also count 1, 2, 3, 4. How many defects do I have? 1, 2, 3, 4, 5, 6, 7, something like that. That's also possible. But that's a discrete kind of chart that you would have. So you have different types of control chart depending on what kind of thing you're measuring in there. All right. Now, what is crucial is that you understand that this process chart is only focusing on the process. It's not focusing on what a customer wants. It's simply focusing on, I have a process, I have a machine, I have operators, they have a certain level of working, and am I still meeting whatever I put in there, right? That's the thing. Right. Of course, you know, this is not good enough. This is important, right? It is important that you know that your process is still stable. Remember, you know, a steady state system? Remember the steady state system I told you about? The idea would be, if this is the input, I need to be able to predict what is going to be the output. And I'm in a steady state system. This is required, a process chart like this process control is required to make sure that my system is steady state. I need to be able to predict if this is the input, this is going to be the output. Okay, the output in this case is not one dot, it's an area, right? It should be in this area. That's the idea. All right. Now the question is going to be, all right, well, maybe my customer wants something different. The question is my process capable of meeting the requirements for my customer? That's the topic of process capability. See the difference? So you have a topic of process control that simply specifies, do I stay within my control limits, my natural behavior of my process? That's process control. Talk about process capability. I'm going to check whether my process that I have is good enough to meet my customer requirements. Now the specifications become important. All right. So Taguchi also said, you know, there are two specifications limits, a lower and an upper, right? And the idea would be that hopefully we remain within there. But if this is my process diagram, you know, if this is what happens in my process, then I see sometimes I go outside of the limits. So in this case, maybe my process is not 100% suited for my specifications limits, right? You can see there is a chance that I might produce something that's not within the limitations of what my customer wants. Okay, right? So these would be rejects. If I measure this, whatever it is that I measure over here, right? I'm not sure what the value is. But if I would measure it over here, my customer would say, I'm not going to accept that. And if I would measure it over here, I'm not going to accept that. Right? My process might still be in control, right? My process is in control. It's predictable. The only thing is the output doesn't always meet my specifications for my customers. All right? Okay. This is the idea of what Tokushi says. And now we can make some. Now we can make some calculations.
Already.
All right. There you go. See, there you go. I knew it. I'm gonna skip this one. Now I'm gonna skip that one. You can check it out for yourself, looking at the time. I'm gonna explain it by an example. All right. So, what you see over here is a normal distribution. See that? It's a bell-shaped curve, right? And I measured what's the average of this process. The average is, it's a length, I don't know, or maybe it's a diameter. It's a diameter. Let's call it a diameter of a hole, right? 10 meters, 10 millimeters, sorry. That's the average. The average, if I drill a hole, the average diameter would be 10 millimeters. It's the worst, it's a bad process, by the way, because this is a large difference in there. But anyway, it's just for example, right? And I have a standard deviation. I looked at the past, I measured all the diameters that I've drilled in the past, and I see that my average distance to the average is 1 millimeter, right? So my standard deviation is 1 millimeter, okay? And I know it's normal distributed, a nice bell-shaped symmetrical curve. Very good. So the average is 10, and my standard deviation is 1, and then I know that this area, plus or minus 3s, 3 sigma, 3 times the standard deviation, is the 99.7% that we were talking about. That's the area, okay? So this is a result of my process. There you go. Well, my customer says, I only accept holes that are within 7 and 13 millimeters. These are my specification limits, right? It's got nothing to do with the process, it's what the customer wants. It has to be within 7 or 13 millimeters. Okay, how well does my process fit my specifications? That's what capability calculates. All right, what I can do is, I can calculate something like this. This makes sense. Look at this. It's how large is this area? That's USL minus LSL. That's the area that my customer finds acceptable, right? The range. And I can look at 6 sigma. 6 times standard deviation. So that's the area that 99.7% of the time I cover with my process. All right? Okay, well, let's do that. So USL minus LSL is 6 in this case. And 6 times the standard deviation in this case is also 6. 6 times 1. Which gives me a capability of 1. CP of 1. This is the definition of CP. All the formulas that I'm using is a gift from me that you're going to get at the exam in the appendix, right? So in the appendix, I'll give you all the formulas. So that you know.
And what does that number exactly mean?
Well, it means that it covers, in 99.7%, I'm still good for my specifications, for my customer wants, right? That's what it says. This is pretty good. I have a pretty capable process in this case, right? It covers as long as I keep my process in control. Most of the products that I produce, by far, are going to be within the specifications.
So below 1, you'll be spamming out of control, and over 1, that means it's very in control.
No, 1 is
So CP larger than 1 is you really without any risk. So the larger CP gets, the better you score, right? The lower CP gets, the less perfect you score, right? The lower your score is going to be, because you're going to have a lot of products that are outside of specification. So I'll show you a different example. What if my specifications would be this?
0.
See that? So if my specifications is going to be between 9 and 11, guys.
0.5.
Please. So if my specifications are this, I only accept between 9 and 11, they have the same process, right? It's the same process. I didn't change the process. Same process. So what is the CP now? Well, the CP now is only 0.33.
And that's better.
And that's worse. This is better. This is worse. The chance that you're going to produce something outside of my specification limits is higher than in the previous one.
Sorry.
Right? So the CP,
70%
which is how wide is this area compared to how wide is this area, gives me an indication of how well my process fits the specifications of my customer. It's the process capability. It also means, by the way, this, right? If my S would be 0.5, right, with an average of 10, then this is a very good process, right? This really fits nicely what I require. The probability that I ever produce a product that's outside of the specification is really low, as long as my process stays in control. Because in this case, if you calculate, right, this is the outcome. It's 2. You're really safe if you have a value of 2. You're really safe. Value 1, you're pretty good, but only 99.7% of the cases. It sounds like a lot, but if I produce 200,000 products a year, there's still a lot of products that are outside of the specification, right? It depends on the volume, whether 99.7% is still okay. If you produce a lot of cars worldwide, having so many cars that don't have a working braking system, I don't know. That doesn't sound like you want to go for that.
Is one more than enough?
No.
Just
No, this is what I meant.
Depends how
What I
many
mean, just it depends on how many products you produce in a year. And if the volume is high, then 0.3% is still a high number,
That's,
right?
usually-
0.3% outside of the range. It's still a high number.
You usually get 1 if the limits of the USL and the LSL are right at the 3 standard deviations.
UCL and EL, yeah. Then it's 1, and it's always 1. Yeah.
So if you want to make 3.1 million boxes, then 5% error rate they told us is quite high.
Yeah. True. Yeah. But this doesn't show everything yet. Sorry. You had a question.
The more the better.
Yeah, the higher the better. Well, yeah, but there, of course, yeah, from a quality perspective, yeah, it is. So, you know, if your CP is 3, it's even better than 2. The only question is probably my process is going to be more expensive. Very likely that my process is going to be too sophisticated for what I need it for.
Yeah.
Right? So 3 and 4, you know, I don't see it often. But it probably means that I have invested too much in my process, right? It's not necessary for my customers. You know, good enough is good. Remember that? Good enough is good. Don't overdo it. That's the idea. Good enough is good, right?
Yes.
Okay. Now the thing is, I made an assumption with these calculations. The assumption that I made is that the average was right in the middle of the specification levels. Right? I put it right in the middle. That's nice, but that's not always true. Right? Could be this.
But what difference does it
Well, calculate the CP. What is the CP? Use the formula. What is USL minus LSL? 6, right?
make? Yeah,
Okay. What is 6S?
3.
No, 3. So my CP is 2.
Yeah.
It looks like a perfect process, doesn't it? Is it?
No.
But there is some percent.
But it's CP 2 is really good, isn't it?
Maybe we should
It's-
use 12.
Why is that?
With a sigma, I think. Something with
Yeah, the
precision.
thing is, it's not right positioned in the middle, right? Because it shifts to one side.
That means
And the
that
only
you-
thing that you compare is
Yeah.
this to this. This is what you compare, but not where it's positioned. Only the size of the whiteness of the curve. That's what you measure.
Yeah,
That's
but-
what in the CP.
You can increase the width, so.
Well, of course, we can check on this side and this side.
Yeah, so
So
that
that's the next step that they would do.
so that could help you with the improvement. So you already know that you can hold like bigger than what you actually should hold, make.
Well, well, at least you know that your process is somewhere to the right hand side. You need to shift it to the other side, to the left hand side somehow, which might mean simply checking something on the parameters. Maybe that might be helpful. But you can calculate, you can show it whether you have this issue or not, whether it's right nicely centered in the middle or not. And it has to do with, sorry.
Why do it has to be in the middle?
Well,
If it's meeting the requirement.
if you measure this,
Yeah, it's meeting the requirement.
yeah, well, in this case, the probability of getting, you see that 3S is already outside in here, right? So the probability that you're going to produce something outside of there is larger. You don't have the 99.3% anymore. It's actually lower than the 99.3%.
What about if it's not centered in the middle, but it's a little?
Well, that's possible. It doesn't have to be exactly in the middle. That's not necessary. That's not what I'm saying. But what you could measure is how skewed is it, right? So is it too much out of the middle or not? And what you're actually talking then about is CP is about precision. It's about, you know, how precise. If I hit again, is it almost at the same spot? That's what CP tells. But it could be, you know, this is very precise. It's only not accurate. It doesn't hit what I want to hit. It's very precise, but it's not good enough. And of course, you know, this is better it's more accurate. It's near where you want to go to, the bullseye. But the thing is, it's not precise. So every once in a while, we do have actually you want to have these dots right here, right in the middle. That's what you want to have.
That's what you want to achieve.
So you want to have a precise and an accurate process.
Maybe explain that.
So how inaccurate actually is this? This is the way to calculate that. So what you're going to do is you're going to calculate two capability numbers, CPL and CPU. CPU for the lower limit and the CPU for the upper limit, right? So it means for the lower limit, what you're checking is how far is this distance compared to 3S. So you only look at the left-hand side from the average. How far is this distance compared to 3S? That's pretty safe, right? It's very unlikely with this data that you're going to create something which is lower than the lower specification level. Very unlikely that's going to happen. And that's true, right? So if you calculate this, this is going to be a very high number. But you can also do it on the right-hand side. It means this is the area which I have available on the upper limit, and this is 3S. Right? So let's fill it in for these numbers, and it gives you this, right? So if my X average is 12 millimeters, my LSL is 7 millimeters, it means that X average minus LSL is 5. My standard deviation is 0.5. 3 times 0.5 is 1.5. This gives me a CPL of 3.33. It's a high number, that's okay, right? We're safe. We're far above the 1. We're pretty good. We're doing pretty good. Now let's take a look at the other one. On the upper side. USL minus X average is this area, right over here. It's 13 minus 12 is only 1, right? S is 0.5, so it says 1 over 3 times 0.5. 1 over 1.5, which is 0.67. This is lower than 1. Remember, the smaller the CP value is, the worse my system is, or the worse my system fits the requirements for my customers. Then I take the minimum of those two, and that tells me something about how accurate I am, how far away am I from the average. And this shows that my CP is still 2. Remember, CP is still 2. That's good. Don't have much range, much variance in there. That's pretty good. The only thing is, whoops, I'm on the wrong side. I'm on one side. I have a problem on the upper limit. That's what it says. 0.67 is below 1, and you don't want to be there. And that means that if I adjust parameters in my process, I might be able to shift the entire curve to the middle. That will be good, you know. But I have to think about what can I do to meet better those specifications. That's what you need to think about. I don't know. Depends on the process that we're talking about. What kind of measures you should take. Does it make sense?
Yeah.
All right. Okay. So this is about how precise are you. That's the CP value, and the CPK is accuracy. All right? Cool. Now you may have heard of Six Sigma. Have you heard of Six Sigma processes? You may have heard. You're going to learn also about Six Sigma processes. A process is called a Six Sigma process. You know now what Sigma is, right? Sigma is standard deviation. So a process is called Six Sigma process if on one side, or on this side, on both sides, there are at least 6 times sigma, 6 times the standard deviation until you hit the specification levels. That's pretty strict, isn't it? Think about that, right? That's really, it's not 0.3% that's outside, it's 0.000 something. Where would they use well, there are a lot of companies that require that level. You know, if it's something life, if it's really crucial, these specification levels is about saving life or you know, facing fatal accidents, you pretty need to make sure that you don't have any product that's outside of the specification limits, right? In aircraft industry, they use Six Sigma. in the automotive industry, they use a lot of Six Sigma requirements. They want to have processes that meet this requirement. This should be at least Six Sigma. Getting there is difficult because you need to do changes in your process, right? So you need to probably narrow down. You're not going to ask your customers, well, also accept that, right? That's one way of getting Six Sigma, right? Customer, don't be so difficult, right? Accept that as well. No, that's not what you want to do. What you want to do is, if the customer wants this, I need to narrow down my process to make sure that it meets this Six Sigma requirement. Okay, think about what the CP value is if it's Six Sigma. Right, it's what is the CP value for Six Sigma? This is 12 Sigma, right? And you divide it by how many times S? 6 times S. Yeah. The CP of 2. CP2 means the Six Sigma process. Okay? And then hopefully the CPL and the CPU also are not different. That's the Six Sigma process. Now you know what a Six Sigma process is. To get there, you need to do a lot of things. But that's what we mean with Six Sigma. All right. So the assumption that we usually make for these calculations is we do assume we have a statistically controlled process. We could use, for instance, a control chart, and we assume that they follow kind of a normal distribution. Otherwise, it's not always plus or minus 3 sigma. If it's not normal distributed, it will be a bit different. We assume that usually that's the case. I want to warn you. I think I explained it, right? And I think you got it. I hope. But this is really crucial. Don't mix up the control limits, the control levels, UCL, LCL, with the specification limits, LSL, USL. Specification limits are for the customer, right? Control limits are for your process, whether it shows the normal behavior or is something extraordinary in your process. Okay? So that's crucial that you make a distinction in there. And also companies make those mistakes. They make the mistakes. They create control charts with specification limits, but you shouldn't do that. You should create control charts with process limits, control limits. Okay?
Yep.
All right. That's it. Check out the, I'll make sure that there's a connection to the YouTube movies. Yes. The ones that I skipped, you can check it out for yourself. All right?